First thing is that I noticed on our syllabus, we have an exam next Wednesday. My intention had been for all of chapter 13 to be on the exam, but we are running behind. And unfortunately, the last 3 chapters are really important content, especially for those of you that are going on to organic chemistry, because all of the information on kinetics and equilibrium and acids and bases come up again and again in your future classes, both the chemistry ones and the ones where there's overlap between chemistry and biology for those of you that are particularly into the biomedical or the biochemistry majors. So yeah, we're going to have to kind of move quickly through that material, which means I'm probably in the next several chapters not going to spend as much time on class on going through problems. I will post online examples. I will either do them myself or find good examples online of people going through problems, but I'm going to rely on you to work through those after class time so that we can get through all of the material. So you do have a vocabulary assignment due tomorrow. I saw some of you already turned it in, so thank you. For Friday, I'd like you to read the first 3 sections of chapter 12, and then I will post a prepare to learn for the beginning of chapter 12 so that you know which content is going to be relevant and going to be discussed on Friday. So any logistical questions? Yeah.
So we're still having the test next week?
Yeah.
Part of 13.
Yeah, it'll just be part of 13. It'll be all of chapter 11 and part of 13. So I am going to include some of the interparticle forces stuff on the exam. There are some people who were kind of struggling with that a little bit, and I want to make sure that we've gone back and looked at that. And so that's what doing your exam corrections should be helpful. So make sure you're not just copying down what the answer is, but you understand how to get to that answer. There will be a couple of questions about naming the forces, but the main idea I want you to have is if it is a stronger force, I'm likely to have a higher response on melting point and boiling point and surface tension and those things. And the only one that is reversed is vapor pressure. I have some practice problems up here. If you struggled with the back side of this, you may want to look at these practice problems. So if you were not here last Friday, these were the problems that we worked on in class on Friday. So I'll put that there. And these are the ones that are some new ones. So as you leave class, you can look at those. All right, we are going to switch gears now and go to kinetics. Okay, when we left off on Monday, we were talking about the things that affect kinetics. So we said kinetics is the rate of a reaction, or talking about reaction rates. And those rates are going to depend on temperature and concentration, and the physical state. And we left off with the question why. And this is going to come down to, why do reactions happen? Well, the reason they happen is because in order to interact, the molecules have to run into each other, have to collide. So it's all based on collisions. The more often molecules collide, the faster the reaction is going to go. So if we think about temperature, higher temperatures are going to mean the collisions have more energy. It also means that the molecules are doing what? Moving how? Faster. So the faster they are, the more often they're going to collide. So they're going to collide more often, and they're going to collide with greater force. And the greater the force, the more likely they are to react. So as you see on the side, it says an energetic collision leads to a product. And then the bottom one says no reaction, they're less energetic. Okay, the other factor we looked at was concentration. Higher concentrations mean more opportunities for collisions. Okay, crowded room, you're more likely to bump into somebody than you are in a pretty vacant room. And then we also talked about state. So I talked about how solids just are hard to mix things together. But also if we think about things being in the same state, so two liquids mixed together, or an aqueous solution where we have dissolved particles, they're all in the same place, so they can interact. If they're all gases, they can interact. So if they are in the same state, they can mix and collide more often.
So you said, like solids are harder to mix, but is there like, times when like two solids will just mix on their own?
Yeah, so actually when I was in graduate school, I did solid state chemistry. And so this is all about doing reactions between solids. And so the idea with a solid is that in order for it to be a solid, you have several of the same particles together, which means the particles that are on the inside are not interacting with different particles. So the bigger the particles you have, then you have a lot more on the inside. It's harder to interact. So when you divide that up, like in a powder, it's much more reactive. And so, for example, aluminum powder, we use that with our summer camps to make fireworks. And we ran out of some a few years ago. And so we had it shipped to us, and it was a bottle that was about the size of a water bottle. But it came to us in a box that was like this. It's huge. Okay. And so it was in a canister that was padded inside the canister, and then outside it like had a huge, like a layer this thick below it of styrofoam peanuts and a layer above this thick, completely surrounded. The bottle itself, I can't remember exactly, it was like 20 bucks. The shipping on it was a couple hundred. Because when we have powdered metals, they react very readily because you've divided them up into such small pieces that there are fewer inside particles and more outside particles. So the key to getting solids to react is high surface area. Good question. Okay, so we're going to talk about reaction rates. We have to know somehow to measure this. Okay, so it's a rate. So we're going to be looking at something progressing over time, right? If we're looking at the rate of speed, we know it's distance divided by time. But this isn't how far we're going, so we have to measure something about the reaction. So what we measure is the concentration of the chemicals. So we know that in a reaction, the product is appearing. Okay, and so its concentration is going to get larger and larger and larger as the reaction progresses. And we also know that the reactant or reactants, depending on how many there are disappearing. They're being consumed and turned into the product. So we can measure either one of these. And the reason why we don't always do one of them is the way that we measure concentration very quickly can depend on what properties the chemicals have. So you all did this lab a few weeks ago where you dissolved copper and you got this nice blue material and you put it in the spectrophotometer to measure the absorbance, right? So there are machines that you can just leave that in there and then over time it will take several measurements of the same thing. And so you can see the reaction progressing. In fact, you'll do something like that in a couple of weeks with crystal violet. So if we have a colored compound, that works really well. But if our reaction doesn't involve colored compounds, then we have to have some other way of measuring concentration. So we pick a chemical that it's easy to measure the concentration, and that's the one that we'll monitor. Okay, so what do we do with these numbers? We plug them into this formula. And so there's a constant that ends up being involved in here, but we're going to leave that out for the time being. So that's why I have kind of the wavy line. But we're looking at the change in product over the change in time. And because that's increasing, we use a positive. We look at the change in reactant over the change in time. And because the reactant is going down, that change will be negative. So we put a negative out front to cancel it so that the two things will be equivalent. So they both end up being positive numbers, but the reason why we have the negative out front is because that changes. All right, and so notice we have kind of a notation here of square brackets. Whenever we put square brackets around a chemical, oops, it was not on this one. Square brackets around a chemical means molarity. Molarity, I can spell it. All right, so from here to the end of the year, we're going to be using these square brackets for quite a few things. So this is molarity. Molarity is moles per liter. Okay, so this is the one that we see most often in lab. All right, so on the packet that I handed out to you, you should on one side see a graph that looks like this. Now it also has some data next to it. I'm trying to save space by putting these two things in here. This over here is, I believe, a gas chromatograph. Oh no, those are liquids. Liquid chromatograph, and so that's another way of measuring concentration. That's why I have it. But we're going to focus on this data right now. So we have two things going on. One line is going down, one line is going up. And so the line going down is C2H4. Is that a reactant or a product? So if we look at the top of the graph, there's the equation. That's a reactant, right? So since it's a reactant, we can see over time its concentration is going down, okay? And then O2, reactant or product? That's a product, so its concentration is going up. Now, if we look at the O2, is the rate that it's increasing steady? Is it the same rate the whole time? Okay, so we know it's not steady. How do you know it's not steady? Not a straight line, okay? And so you can make some guesses based on the curve about what that is, but the point is that it's not a straight line. So we know intuitively that a straight line means it's a steady rate, and a curved line means not steady. So for both of these, is the rate faster at the beginning of the reaction or at the end of the reaction? Beginning, okay? So rates are faster when our curve is more vertical, And as it becomes more horizontal, that means the rate is slower, okay? So we can use the slope of the graph to tell us what the rate is, okay? All right, so you should have this data next to your graph. I don't know why my source for these things did this, but this is looking at the concentration of ozone, which is the other reactant. But if you compare these numbers to the data points, they're the same data points as for the C2H4, so they put exactly the same concentration in the two of them. So for whatever reason. Okay, so first thing that we can look at here is that the concentration is going down. So we have those data points and we have times. Now, this does not allow us to directly pull out the rates, right? We can't just pick one of those numbers and say 1.95 times 10 to the minus 5 is a rate, correct? Yeah, because we want to look at that change. So when we find these values, what we do is we look at the difference between different sections. Okay, so this data is going to get squished on the next slide, but it's still the same data. Okay, so you can still look at your same paper, right? So one thing that we might look at is the overall rate. So the overall rate is from the beginning of the reaction to the end of the reaction. What was our average? So we're going to take our final concentration, 1.1 times 10 to the minus 5, and subtract our initial, 3.20. Okay? And just to save space, I pulled out the times 10 to the minus 5 and put it on the outside, but trust me, the math works. And then my change in time is my final time minus my initial time, so 60 seconds. All right, so if I plug all of that in and crunch the numbers, I get 3.5 times 10 to the minus 7 molarity per second. Okay, so my rate is going to have the units of concentration, because I measured a change in concentration, divided by units of time. For most reactions, that's going to be per second. But if we're looking at a reaction like nuclear decay, sometimes that can take years. Sometimes we'll look at minutes, but usually it's seconds. So this is one way we can look at a reaction, is to look at the overall rate. But that's not necessarily the same thing depending on how long I look at the reaction. Because if I looked at the reaction for 40 seconds, or if I looked at it for 10 minutes instead of just 1 minute, I might end up with a different number. So a lot of times we talk about the initial rate. And so we would approximate this by our first 2 data points. Okay, so what am I going to subtract for my concentrations? What 2 concentrations will I use? So am I going to use this 1.10? No. I'll definitely use the first one. What other one? I'm going to use this 2.42. Okay. How many seconds will I divide by? Just 10 seconds. Okay, so I'm not doing the overall. I'm dividing by 10 seconds. And so I end up with 7.8 times 10 to the minus 7. Okay, so notice that if I'm looking at the overall rate versus just the beginning, I get a very different number. This is more than twice that number. So paying attention to what portion of the graph we're looking at is important. Now, what we'll learn in the next couple of sections is that rather than looking at individual data points, we can kind of take a shortcut if we use calculus. Now, you're not going to actually have to do the calculus. The calculus was done for you, and then we just get this equation that pops out of the calculus. This last one is just kind of to drive home the point that if I'm looking at the last 10 seconds, I also end up with a very different number, and it's a much lower rate. So we don't usually look at the last 10 seconds because, you know, that just depends on how long we're looking at the reaction. All right. Related rates. So this means how is the rate of, say, the reactant related to the rate of the product? Now we saw the two reactants were kind of doing the same thing. Oh, wait, I'm sorry. We're not at related rates yet. We're at the graph. Okay. This is basically looking at the same thing. So this was C was the one that was our initial that we measured by average. A is the true initial. So we do that by finding the tangent line. So remember, the tangent line is what touches the graph at just one point and has the slope at that point. So the slope right at that beginning is A. And so C is the best approximation. That's closest to that. And then B is the overall average. So we calculated that as 3.5 times 10 to the minus 7. And then we look at C as the approximation, and then we have the approximation down here. Now we can also find a tangent line somewhere else on the graph, and we would call that the instantaneous rate. We won't do too much with the instantaneous rate, but it just means that at any given point, what is the rate, or what is the slope of the line at that point?
So D is would be the
D is the instantaneous rate at that point.
And then you said B is what we found last slide.
Yes, so B, the very first thing that we did was find the overall rate. So notice how this is going from the very first point to the very last point. This is the same data. So B was the very first thing that we found, was the overall rate. C was the second thing we found. That was our approximation of the initial rate. And then A is the true initial rate because it's the tangent lines right at that point, rather than taking two data points. Okay, so how are rates related? Well, when I'm making, or when I'm using the same number of particles, which I can see from the equation, I have the same coefficients. Every time I use one ethylene, C2H4, I'm also using one ozone. Okay, so there's 1-to-1 ratio. So the rates of those two would be equal to one another. So it doesn't really matter which one I talk about the rate for because I have the same rate for both. All right, we already looked at that. Okay, so some definitions of things we talked about. Average rate is over a period of time. Instantaneous rate is at a particular moment, and it's the slope of the line tangent to the curve. And then initial rate is also an instantaneous rate, but it's at the moment the reactants are mixed. So if you haven't done your vocabulary yet, these are some terms you should be seeing in the vocabulary. Okay, I want to take a quick look at the next slide, and I think did I give you a copy of this? Is that in your packet? Okay, so this is the related rate. So this is showing how two things are related, and we talk about if they have the same coefficient, then the rates will be the same. If they're different, then they're different by their coefficient. So the lowercase letter in each case represents the coefficient, and the uppercase letter represents the chemical. And so we use this to show the related rates. On Friday, I will show you how you get from one to the other, because it's not real intuitive from this if you're not real up on your math. So we'll go through a quick example of that. At most, there would be one question like this on your test, so I don't ask a lot. Yes.
What did you say the uppercase one was?
Uppercase is the chemical. So like I might have 2 H2O. A would be H2O, lowercase a would be the 2. All right.